Okay, hello everyone. Welcome to another Zoom meeting of MIT Spark Lab. My name is Han, and I'm a PhD student at Spark Lab. It's my pleasure to introduce our speaker today, Luca Ballotta. Luca has just obtained his master's degree in automation engineering from the University of Padua at Italy, and he is currently continuing as a PhD student there. Luca has been a visiting student at Spark Lab since February this year. Luca's research lies in distributed and sparse estimation and control for network systems. In particular, he's working on control of processing systems subject to communication and computation delays. Today, Luca will talk about his recent work on computation-communication trade-offs and sensor selection in real-time estimation for processing networks. I'll give the stage to Luca, and let's welcome Luca to give his talk.
Okay, thank you very much, Hank. This work is on estimation of network control systems subject to computation and communication delays, and jointly the sensor selection, which arises in the context. Okay, so just a quick motivation for this. We are thinking about network control systems. So like target tracking or smart grids, autonomous driving, and so on, in which we have multiple devices communicating each other. And in particular, we are focused on real-time systems. So we may think in particular about like this or this as dynamics. And our main concern, our main challenge we are facing is the delay. In particular, the delays arising on the one hand from communication constraints, which we call communication latency, and it's basically the time that information needs to takes to travel from one node to the other in the network. And then we have computational constraints, which are mainly due to the hardware of the single devices, which induce some computational latency. And this latency is mainly due to the local preprocessing, which is performed at each device. So for instance, a drone or a mobile robot making some computations and so on. So as said, we are mainly interested in a real-time system, and in particular, so-called time-critical applications where information needs to be delivered timely in order to avoid errors which may be very serious for the application itself. For instance, here there's a very dumb example of an autonomous vehicle going onward. And of course, if information is not delivered from the sensor to, for instance, a central controller of the vehicle, the estimation of the position of the car can only be inferred by odometry, and this in open loop, and this leads to larger inaccuracy in the in the estimation of the position of the car. So we want to design these delays, which are unavoidable, in order to provide the system with the best possible estimation. So as said, of course, latency is unavoidable, but we mainly play on this that we call computation-communication trade-off, which arises in particular in networks where smart sensors are present. So smart sensors are opposed to classical sensors. Say classical sensor mean that these sensors can only acquire some measurements, like in this case images, and transmit them over a wireless channel. In our case, we are mostly interested, of course, in wireless communication. And this, of course, takes time for the data to be delivered over the channel. But on the other hand, the sensor, other than the time needed for the physical data acquisition, it doesn't spend any time. On the other hand, we are interested in networks where smart sensors are present. And so smart sensors can choose to preprocess their data in order to extract useful information, which is also compressed generally, to transmit over the network. So here we see a trade-off, which is basically if I choose to preprocess more time at the sensor side, I can reduce the time needed for communication, but of course I spend some time in order to do this very preprocessing. And so this is a trade-off which is needed to which has to be addressed for large networks. So the first idea is that to derive is quite simple mathematical model for these processing networks. which takes into account the delays. And on the other hand, we want to address optimal estimation in this work. So in particular, dealing with the delays and trying to address the computation-communication trade-off. So here this is just a representation of the network we are going to address. We have this bunch of nodes, which are smart sensors. And in general, each node may have a different computational delay, so a different preprocessing of the data, and also therefore different communication delay needed to transfer the data over the channel. Then in this framework, we have a star network. And so all sensor data are fused at the central station. And we are also going to consider the delay due to the fusion. So central station, as this fuses all the sensory data, performs a processing, and this also induces a delay. So let me start describing the mathematical model of the network. Of course, I stressed that the system is dynamical, and the dynamics of the system, of course, plays an important role in choosing in designing the optimal preprocessing that is needed to sensors. So as for the smart sensors, we imagine to have a network of heterogeneous sensors, which for simplicity are also independent. And each sensor comes with a preprocessing delays tau I, which is to be designed. So this is our very simple model, linear time invariant model. Each sensor has its own transformation, state output transformation. So this zeta is the observation of sensor I. And in particular, the preprocessing delay is going to impact the observation of the sensor, and in particular is going to affect the measurement noise in a way that I will immediately explain. So the idea is that each sensor can perform some anytime algorithms. This is an example of anytime-like neural networks, which can trade the inference time and the complexity of network in practice. And so for each sensor, we may choose how much preprocessing to perform. And in particular, the more a sensor is allowed to preprocess the data, the more accurate the output will be. And so this is mathematically encoded by saying that the inaccuracy given by preprocessing the data is decreasing with the preprocessing delay. And so in practice, we are mirroring this descending behavior in the inaccuracy of the preprocessing, which is given by the variance of the measurement noise. Okay, so as regards communication, we have this main assumption that each sensor can transmit its data with the probability that the data are correctly received as the central station, lambda I. And so its opposite, 1 minus lambda I, may be addressed as a packet loss probability. And also, each measurement which is correctly received is received with a delay tau Ci, which is so different for each sensor. So the simplest model is that these delays are constant with respect to the preprocessing delay. And so in practice, if delays are constant, the preprocessing which is performed at each node doesn't affect the communication delay. On the other hand, we have this other relationship, which is the one I was speaking about before when talking about the computation-communication delay. And so with this assumption, the more time a sensor is allowed to preprocess, the more the data are compressed. And so the more delay I spend on preprocessing, the less delay I have then for communication. And so this addresses exactly the communication-computation trade-off as before. Last, we have the central station, which is in charge of fusing all sensory data. So we may imagine all this bunch of sensors communicating to the central station. And so each sensor induces some delay at the central station. And the model for this delay is similar to the analogous in practice to the communication delay is either constant with respect to the preprocessing or decreasing. And so this is, of course, always paired to the concept of compressing data. If I preprocess more at the sensor side, I can compress data. And so then my central station needs to perform less effort, and so takes less time in order to fuse all data. So at the central station, we have a total fusion delay, which is in practice only the sum of the fusion delay induced by each sensor. And so this is increasing with each sensor which is present in the network. And this is a representation of the overall framework. So we have, this is central station, which is receiving data from sensors. This is any sensor I, which is transmitting data. So each arrow is a measurement, which is transmitted to the central station. And here, for simplicity, all measurements are correctly received at the central station. So you see that if sensor I in this moment takes a measurement, then takes this time for preprocessing and delivery of the data, and only here this measurement is collected at the central station. So we may imagine that at this point, the central station starts to perform the fusion of all available data, and then after this time, the estimate of the current state is available. So notice that at time t, the central station cannot exploit all measurements which are being collected by sensors by time t, but at this time, it can exploit all measurements that are being collected until this very instant. And so in practice, the central station must stop collecting data at this point because all this time is needed to transmit the data and perform the fusion. And so in practice here, the central station will have computed an updating estimate, and the estimate of the current state needs a prediction to be correctly computed.
Okay. Question.
Yeah, Hank, sure.
What kind of time delays are we talking about? Is it like milliseconds or microseconds or just?
Okay, so here there are no particular like time units involved, but we may imagine that these time are more or less comparable with the sampling time of the system. Oh. So we are thinking about a discrete time system, of course, in particular because we are dealing with the estimation algorithm, and so for the work to have some sense, I would say these delays must be more or less comparable with the at least the sampling time of the system. So if we have like cameras collecting data at I don't know 30 or 40 frames per second, we have an acquisition times in the order of some bunch of milliseconds, and so we may say that these delays are also in the order of milliseconds.
Okay, thanks.
Okay, thanks for the question. Okay, so now this is our setup for the problem. So we are dealing with a discrete time LTI dynamical system, which for simplicity in this case is not controlled, but we're just thinking about the estimation. And we have this heterogeneous sensor network, which is gathered in this equation. And the measurement noise is affected by all the processing delays of the sensors through, in particular, the measurement noise variance. And so we want to assess the performance of the Kalman estimator when when the filter is fed with outdated measurements. And so a prediction is then needed to restore the current state. So the problem formulation is the following. We have this sensor network and system, and we want to minimize this cost function, which is the steady state variance of the estimator, of the estimation error. And we want to minimize this with respect to the the sensors. So V, this calligraphic V is the set of all available sensors, and this calligraphic S is the sensor that we are selecting. And also we want to select the preprocessing delay, so the computational effort which is required at each sensor. And this tau total tells how old is the estimation which is computed with the available sensor data. So this is this notation is just a notation to say I have gathered data until this time, so k minus tau total, for instance, and I want to recover the state at time k. So the first case study is very simple, just to gather some intuition about the problem. So we address a scalar continuous time system monitored by a homogeneous network. And by homogeneous network, we mean simply a network composed of identical sensors, which therefore have the same model. And also we may assume the same delays. And also for this first intuitive result, we don't address sensor selection, but we want just to select the optimal preprocessing delay. And so the very simple first approach is to say, for this continuous time scalar system and homogeneous sensor set, we want to find the optimal preprocessing delays, the optimal preprocessing delay which affect each sensor in the network. So these are then just the model we are using. This is for the communication delay constant is just this constant, and the same for fusion delay. And instead, for the computation-communication trade-off, we are using this this function, which is simply an inversion or proportionality between computational delay and communication delay. And then, since the network is homogeneous and we are dealing with Kalman filter, this is in practice the same as considering a single sensor with variance reduced by a factor which is the number of nodes in the network. So anyway, from a mathematical point of view, we are just focusing on one single sensor and selecting the optimal preprocessing delay. So this is the mathematical framework for this for the single sensor problem. The variance is always thinking about the least square framework, just as a mathematical convenience. We model the accuracy improvement of the sensor preprocessing with this inverse proportionality. So this is the inaccuracy, of course. This is a variance, an error variance. So the more time I spend on preprocessing, the less inaccuracy the output data have. And so this is the Kalman optimal estimator with the this is the classical error variance dynamics, and we are considering the steady state case. So this is just a 0. And now turns out, of course, that the estimation error, which is only performed with the sensor data, is decreasing with the preprocessing delay, but it's outdated. And so a prediction is needed to restore the current state. So of course the prediction error is increasing with the delay, because if I preprocess, for instance, 1 minute, then I need to recover 1 minute in open loop prediction to recover the current state. And so this, of course, leads to a trade-off within the sensor estimation, which we call latency accuracy trade-off. So there's a trade-off between the preprocessing delay, so the effort, the computational effort which is required at the sensor, and the overall accuracy, which at the end of the day, the estimation has. So it turns out that there's a unique minimum point for this cost function, both for unstable and stable systems. And so the take-home message here is very simple, and it's just for the single sensor scenario, there's a unique optimal amount of preprocessing which has to be performed at sensor side in order to get a good overall estimation, considering both the time needed for processing, the time needed for communication, so to transmit data to the central station, and finally, also the time needed at the central station to compute the estimate and project in open loop the outdated estimate of the state. So this is just an insight instead of the performance with the number of sensors, because of course this is a traditional framework where the adding sensors doesn't have any drawback, because there's no fusion delay. So even if I add a lot of sensors, the central station in practice can perform all computations with negligible time. But instead, in this context, we are considering the case where each sensor adds some fusion delay. So the more sensors are added, the more effort is required at the fusion station, and so the more time is needed to to perform the data fusion. And so in this context, it turns out that there's actually an optimal sensor amount, which is in general not equal to the maximum sensor amount. And so this is exactly because of this trade-off. The estimation error is decreasing with the number of sensors, but the prediction error is increasing with the number of sensors, because each sensor requires some time, and this time needs to be then recovered with the open loop prediction. And so this gives some motivation for the sensor selection.
I have a question.
Yeah, sorry, thank you.
Go back to this, this slide. So if I'm understanding correctly, the first case you consider just one single sensor, and then you say that there's a unique processing time that achieves the minimum prediction error. And then here I have homogeneous network of sensors, and this is there's a unique number of sensors that achieve the minimum prediction error, right?
Yeah.
This means that there's an optimal number of sensors S star, and there is an optimal processing time tau star. Does this mean that this tau star and the S star together solve the original problem? Is it correct, or because I'm fixing number of sensors, or I'm fixing the processing time, and then I get two optimals, S star and tau star? But is this equivalent to saying that S star and tau star together as a joint solution minimize the original, minimize the prediction error? Is this correct?
Yeah, okay. So in general, no. So in general, this tau star and S star are dependent. This first problem here is, as you were saying before, imagine to fix a certain amount of sensors, of identical sensors, but then the mathematical formulation, the problem can be recast as a problem on the single sensors. So this is a solution. So this is a tau star, you may say, when we have fixed the amount of sensors. Then this what happens instead, as you were saying before, if we fix the tau. So for each of these marks, you may imagine that there is a specific tau star. So the preprocessing delay is fixed for each sensor, and then we are increasing the number of sensors in the network. So in general, these two optimal values are dependent. And on the one hand, this first approach was just made in order to gather some insight about the optimal preprocessing delay, while instead this one was to gather some insight about the existence of this optimal sensor amount. So in general, they are dependent, and the tricky part here, of course, is that although you may formulate this problem in a continuous form, because originally, of course, the preprocessing delays are discrete values, but you may relax this hypothesis in a continuous time framework, saying that also the preprocessing delays are continuous. But of course, you may not say the same for the sensor amount, because of course sensors are a discrete quantity. And so this is the tricky part, and this is the reason why we didn't tackle the problem of trying to optimize at the same time the processing delay and the number of sensors.
Okay, so for each of the in this graph in the left plot, for each of the red square you plotted here, the tau star for each of the red square is the same, right? Not different.
It's the same, exactly. So here we are just imagining of having all a bunch of identical sensors, all already set with the same preprocessing delay, preprocessing amount, and then we are just increasing the number of sensors.
Okay, got it. Thank you.
Okay, thank you for your question, Han. Yeah, okay, so in general, the original optimization problem is combinatorial, so it's NP hard. And the thing is that here we are both dealing with the selection on the sensors and on the preprocessing delay of each sensor. And both these quantities in the general case are discrete. Yeah, sorry, this shouldn't be an R, should be an N, for instance. So tau I are just multiple of the sampling time of the system. So we treated this with a simple greedy approach. The idea being, the idea behind this being, on one hand, the quasi-convexity of the cost function in the simple case, which is this. And so the idea is that the one-dimensional profile of this multi-dimensional cost function is quasi-convex. And on the other hand, we have sensor selection, which is motivated by this very remark we made about the optimal sensor amount S star. So here the algorithm is actually very simple, and this just we start with one sensor and try to add one sensor at a time. Each time computing the optimal sensor, computing near optimal delays and near optimal cost. And so we add one sensor at a time until the cost cannot be decreased anymore. As for this computation, so when we have the computation of near optimal delays, when we have one tentative sensor subset, we exploit the idea of quasi-convexity, and it turns out that at least heuristically we may see that each dimension of the cost function is quasi-convex. And so instead of when we have one subset of sensors, instead of optimizing all delays at once, the idea is to optimize one delays at a time, following this one-dimensional quasi-convex one-dimensional profiles. And so it turns out that actually the near optimal delays are quite close to the optimal choice of delays. So these are just some simulation just to give some insight of on the performance. Here you may see that with 6 sensors, 6 heterogeneous sensors, this is the performance which is achieved by the algorithm. This is the performance, the optimal performance. And these other bars are performance of the same algorithm, but where we are neglecting some delays. For instance, here we are saying that all the fusion costs 0 time, and here the communication is instantaneous. And you can see that, of course, the performance here is worse because we are neglecting some feature of the model. And here we are adding different sensors, so with different parameters. But anyway, you see that in general, as we increase the number of sensors, the optimal performance decreases. So the optimal cost decreases because there is more freedom, there are more sensors to choose. And the cost by using all sensors or a wrong selection of sensor becomes higher and higher. In particular, you can see that due to fusion delay, the optimal sensor, or at least near optimal sensor amounts corresponding to green bars, is definitely lower than the overall number of sensors. For instance, with 96 sensors, it turns out that 5 sensor is a near optimal number of sensors in the sense that outperforms all these other choices. Okay, so long story short, we have designed this mathematical model for preprocessing network with delays, and in particular, assuming also that the sensor can preprocess some anytime algorithms for which we can choose the preprocessing delay at each sensor. And from our formulation, it turns out that a continuous time homogeneous network leads to an analytical solution which can give some useful insight on the structure of the problem. Instead, the general setup is combinatorial, and at least in this work is tackled with a greedy approach. And this is just some possible future work to address. So improving the communication model, in particular with unreliability of links and variable random delays. And on the other hand, another idea is to drop the fusion center and so address general networks with the sensor communicating with each other, and replacing the fusion with node interaction. Okay, and this is all. Thank you for your attention. If you have any questions, I can answer.
Luca, I have another question. Can you go back a few slides to the plot where you show the greedy algorithm? Like
yeah, sure. This or this?
Yeah, this one. So
okay.
In this plot, you are continuously adding sensor, right? And then in this graph, it looks like every time you add a sensor, the cost, the arrow keeps decreasing.
Oh, no, sorry. No, maybe here I went a bit fast. So this is okay. So this is these marks are not related to sensors, but to delays. So here the idea is that we are trying. We have a fixed tentative subset we want to assess its performance, and so each of these marks correspond to a different delay. So for instance, here we have 3 sensors. For instance, this axis represents the preprocessing delay for sensor 1. And so here, for each of these red iterations, we are fixing the delays of the other sensors, which in this case are sensor 2 and sensor 3. And we are trying different delays for the sensor 1 till we get to a minimum, which is only referred to sensor 1. So this point is the minimum cost which can be achieved with those fixed delays for sensor 2 and sensor 3, and varying delay for sensor 1. And then we repeat for each sensor until we get to the minimum performance possible after having gone through all the sensors.
Okay, but this is okay. So that's why this is a greedy algorithm, because in theory you should go through each of these sensors like cyclically, right? And
yes, of course, the optimal delays could only be recovered by an exhaustive search, more or less an exhaustive search. Maybe some choices may be excluded, but in general, there's the in general you have to go through an exhaustive search at least for a choice of delays. This is far simpler because it's not exponential with the number of sensor, but it's just linear, and that is the catch.
Yeah. The other question is how do you decide the number of sensors, right? Because for example, if in the set V I have 10 sensors, do you go through all the 10 sensors together? Or no. Do you go through all of them, or you just go through a subset of them? Because this is combinatorial, right? You don't necessarily need all 10 of those sensors. Right?
Yeah, right. Indeed. So for instance, we have 10 sensors, and the idea is that so the idea is that at first we compute the optimal cost by considering one sensor networks. So for each of these 10 sensors, we take one sensor at a time, and we compute the optimal cost, which is like this. Okay. So this is like one sensor, and you compute the optimal cost with one sensor. Then we select, then the first sensor which is selected is the best sensor, so the sensor leading to the lowest cost. And then starting from this first selection, we iteratively try to add all the sensors which are still to be selected. So for instance, imagine that we select the first sensor, then we try to add the second sensor, and we have all a bunch of possible two sensor networks. Okay, and for each of these two sensor networks, we do this with two sensors. And so at the end of the day, we have the best two sensor networks. So the two sensor network with the lowest cost, and we select that one, and we go on until adding sensors doesn't decrease the cost further. And of course, the idea, the rationale behind that is this. So is that because of fusion delays, at some point, adding sensors will only increase the prediction length, and this increasing in the prediction length, so in uncertainty due to prediction, will not be balanced by the contribution of the new sensor in the estimation part. So we start with one, and then we add, and then we stop until we cannot decrease further the cost. And when we stop, that is also the number of sensors that we have selected.
Oh, by the way, can you go next slide? I had another question. You have this next one. Sorry.
Oh, yeah.
You have this true optimum. This true optimum is obtained through exhaustive search by enumerating all possible things. Okay. Okay.
Yeah, yeah. So we designed this experiment with this simulation so that the true optimal could be computed in a reasonable amount of time with an exhaustive search. Of course, when you increase the amounts of sensors like here, or you allow a lot of choices for the processing delay, an exhaustive search becomes infeasible.
Okay, thank you, Luca, for this nice presentation. Yeah.
Okay, thank you, guys.